Hi, this is your video for Chapter 8, and Chapter 8 is about sampling distributions. So we're going to cover everything about sampling distributions just in one big video. The objectives for this are 1. Explain sampling distributions, 2. Identify the consequences of the central limit theorem, 3. Compute probabilities for sample means. So objective 1 is to explain sampling distributions. So the sampling distribution of a statistic, such as the sample mean or the sample proportion, is just the distribution of all values of the statistic when all possible samples of the same size n are taken from the same population. So for sample means, we have the sampling distribution of the mean. That's the distribution of the sample means. And again, we have all samples having the same sample size n taken from the same population. The thing about sample means is that they target the value of the population mean. That is, the mean of the sample means is the same as the population mean. Another way to think about this is that the expected value of the sample mean is equal to the population mean. If we look at the distribution for the sample means, it tends to be a normal distribution. For sample proportions, we have the same kind of thing. And again, a proportion is where we're just looking at the fraction or the percentage of a population that has a certain characteristic. So the sampling distribution of the proportion is the distribution of sample proportions with all samples having the same sample size n taken from the same population. So if you think about taking all the possible samples of size n from a population and then figuring out the sample proportion for each one, in other words, the proportion from each sample that has a certain characteristic, and then looking at all those different proportions that you came up with from all the different samples, here we're talking about the distribution for all of those sample proportions. Sample proportions target the value of the population proportion. That is, the mean of the sample proportions is the same as the population proportion. Another way to think about this is that the expected value of the sample proportion is equal to the population proportion. Again, the distribution of sample proportions tends to be a normal distribution. And we need to talk about a little bit of notation here. We end up using p for so many different things in this course, it's a little bit hard to keep them straight. So in this chapter, we're talking about a lowercase b being our population proportion. In other words, the proportion of the population that has a certain characteristic. And p with a little caret over it, and we usually call this p hat, is our sample proportion. So that's the proportion of the sample that has the particular characteristic that we're interested in. So let's look at some examples of sampling distributions. So consider repeating this process. Roll a die 5 times, find the mean of the 5 rolls and the proportion of odd numbers of the 5 rolls. What do we know about the behavior of all sample means that are generated as this process continues indefinitely? In other words, if we repeat this process over and over and over, what's going to happen with our sample means for the mean of the 5 rolls and our sample mean for the proportions? So here's if we're talking about the means, and again, this is where we're rolling the die 5 times and finding the sample mean from those 5 rolls. So for example, our first sample, we might get a mean of 3.4, second sample a mean of 4.4, the third sample a mean of 2.8, and so on. So we've got every possible sample of size n from the population, and we have listed the mean for every one of those samples. Now our population mean is going to be 3.5. That just means that that's the mean of our possible outcomes. Our possible outcomes for rolling a die are 1 through 6. So if we take this and keep doing it over and over, then in this case, they did this 10,000 times, so they had 10,000 trials of the experiment, and the mean of all these sample means turned out to be 3.49. And again, that's very close to what our population mean would be. And the more trials that we do, the closer this mean should get to our population mean. And if you look at the distribution, so this is the distribution of all the sample means out of those 10,000 trials, this looks like a pretty nice bell curve, so it's approximately normal. Now what if we look at the proportion of odd numbers in those 5 rolls? So we're rolling a die 5 times, and then we're looking at each of the 5 rolls and figuring out how many of the 5 are odd numbers. So we're just looking at that as a fraction or a proportion. Now our population mean for that would be that half of them should come out to be odd numbers. So our population proportion would be 0.5. And again, here we're taking each one of those samples out of the 10,000 trials, figuring out that proportion of odd numbers, and then we're taking all of those values and finding the mean of all those. And in this case, that mean turned out to be exactly 0.5. And here, it's a little bit harder to tell looking at this distribution because there aren't very many possible values. But again, this distribution is going to be approximately normal. Objective 2 is to identify the consequences of the central limit theorem. So the central limit theorem tells us that for a population with any distribution shape, the distribution of the sample means approaches a normal distribution as the sample size increases. The main condition of this theorem is that the samples have to be simple random samples. So here's some points from the central limit theorem. First of all, the mean of the sample means is going to be the same as the population mean. So in other words, our expected value for our sample means is going to be our population mean. So this is the easiest formula you'll see in this class because all you have to do is say what was the population mean. You don't have to do anything to the number, you just write it down. For the standard deviation of the sample means, this one you have to do a little bit with. The standard deviation decreases as n increases. And how we actually get it, this is our standard deviation for the sample means. You take your original population standard deviation and divide it by the square root of the sample size. So you can see looking at this formula that as n gets bigger, that means you're dividing by a bigger number, which would make this overall value smaller. Okay, another point from the theorem is that if the original population is normally distributed, then for any sample size n, the sample means will also be normally distributed. So if the original population had a normal distribution, we don't even have to worry about what sample size we have. Our sampling distribution will be a normal distribution. Now if the original population is not normally distributed, then we do have to think about the sample size. In that case, we have to look at samples size larger than 30. If they are larger than 30, then the distribution of our sample means is going to be approximately normal. If they're smaller than 30, then we don't have any guarantee of anything. All right, here's another example. This was a population that had a normal distribution to start with. So here was the distribution of our sample means when our sample size was 1. And you can see that even this one looks approximately bell-shaped. When n is equal to 10, we get an even nicer little bell shape. And when n is equal to 50, then we have even more of a bell shape for our sample mean. Now this one comes from a uniform distribution where every value has the same probability. So here was when n equals 1. This is what the distribution looks like for the sample means. When n is a little bit bigger, when it's 10, then we're getting a little bit closer to being a bell-shaped curve. When n equals 50, we have a pretty good approximation of a normal distribution. In other words, this is pretty close to being a bell-shaped curve. And finally, what if we start out with a sort of a U-shaped distribution, where it's higher on the two ends and lower in the middle? Still, when n is equal to 10, it's already gone to a somewhat bell-shaped distribution, and when we go all the way to n equals 50, we've got a nice bell-shaped curve. Objective 3 is to compute probabilities for sample means. And this is going to use the same ideas that we used back in Chapter 7 for finding probabilities when we have a normal distribution. So again, if our original population is normally distributed, or if we have a sample size greater than 30, then we can assume that our sample means have a normal distribution. The mean of this distribution is the same as the mean of the original population, so we can just use this formula. So this stands for the mean of our sample means, and this is our original population mean. So they're both the same. Then our standard deviation is our original population standard deviation divided by the square root of the sample size. So here's what our formula looks like. Let's do an example of finding a probability for a sample mean. So assume that men's weights are normally distributed with a mean of 191 pounds and a standard deviation of 30 pounds. At first, we're going to find a probability just like what we did in Chapter 7 that involves just one individual. So find the probability that if an individual man is randomly selected, his weight is less than 176 pounds. Okay, so again, this is just a normal distribution problem. So we have our mean in the middle, which is 191. Standard deviations marked on either side. So if we go down one standard deviation, that would give us 161. And if we go up one standard deviation, we'd have 221. And again, it's a good idea to mark at least those three values on there. All right, so we're looking for the probability that the weight is less than 176 pounds. So let's mark the 176 on here. And then we want the probability that his weight is less than that. So we're going to go from there to the left. And again here, since this is a probability for an individual, we're using just the mean and the standard deviation from the original population. Now since this goes all the way to the left, we're going to use a large negative number for our lower bound. 176 is our upper bound, and then our mean is 191. Our standard deviation is 30. So if you put this in your calculator, you'd get 30.3085, or 30.85%. Now let's look at a similar problem, only one that involves a sample instead of an individual. So find the probability that for a sample of 16 randomly selected men, the mean weight is less than 176 pounds. So the key difference between these two is that here we were talking about one individual, here we're talking about a sample of 16. So we're actually looking at the mean weight for the whole sample in this case. So this is the clue that you're looking for a probability that involves a sample mean. And remember, the notation for a sample mean is x bar. So what that tells you is that we still use our population mean of 191, but for our standard deviation we have to use that formula. That means we take our original population standard deviation and divide it by the square root of the sample size. So we're taking 30 divided by the square root of 16, or 30 divided by 4, and we get 7.5. That's our standard deviation for our sample mean. So that would be sigma of x bar. So here's the difference between these two problems. In the first one, we had our mean at 191, our standard deviation was 30, so our 176 fell halfway in between the mean and 1 standard deviation below the mean. And our probability came out to be 30.85%. Now when we're talking about using a sample of 16 and we're talking about the probability for the sample mean, that changes our standard deviation to 7.5. So notice the difference between these distributions if you draw them using the same scale on the x-axis. Now our 176 is actually 2 standard deviations below the mean instead of being half of a standard deviation below the mean. So that makes the probability much, much smaller. Our probability here is only 0.0228 or 2.28%, whereas in this one it was 30.85%.